So far in all the differential equations we've studied, we've assumed all the functions involved to be continuous. But sometimes there are differential equations where that function on the right-hand side is not continuous. And when we get a differential equation like that, we use a tool called the Laplace transform. So we've previously studied differential equations of the form nth derivative plus something n minus first derivative, etc., plus something y equals f of t, with this function f of t being continuous. Now when f of t is only piecewise continuous, we use different tools. Now piecewise continuous means maybe I'll write PYC for piecewise continuous. These functions look like this. So for every interval we've got a continuous function. And maybe there's some infinite intervals. Now, all the discontinuities are finite. They all happen between the intervals. So something like this is not allowed when we have a function on one interval that goes up to infinity. So there's no infinite discontinuities allowed. If we're given a function f of t defined for t between 0 and infinity, so t positive or non-negative, we define L square bracket f, called the Laplace transform of f, to be the integral as t goes from 0 to infinity of e to the negative st f of t dt. So after we're done integrating t, what we get is a function of s. So let's do a couple examples. So let's look at the simple function f of t equals 1. So the Laplace transform of the function 1, L of 1, equals the integral as t goes from 0 to infinity of e to the negative st times 1 dt. So that's negative 1 over s e to the negative st evaluated from 0 to infinity. Well, that's an improper integral. So we really should write it as a limit, say as n approaches infinity, of negative 1 over s e to the negative st. T goes from 0 to n, which is a limit as n goes to infinity of, let's see, maybe it'd be easier if I wrote this as negative 1 over s e to the st. Negative 1 over s e to the s capital N minus negative 1 over s, and then also in the denominator e to the negative s, or e to the positive s if it's in the denominator, times 0. Alright, now e to the 0 is 1, so we're left with 1 over s here, and then whatever happens to the first limit. So 1 over s, and as n goes to infinity, this exponential in the denominator goes to infinity, and then the fraction goes to 0. So I guess 1 over s is it, because this goes to 0. So the Laplace transform of 1 is just 1 over s. Let's do another example. F of t equals t. The Laplace transform of t is the integral as t goes from 0 to infinity of e to the negative st t dt. All right, now we need integration by parts to do this. So I'm going to write the t first and e to the negative st second, because if we call t u and e to the negative st dt dv, then du equals dt, v equals negative 1 over s e to the negative st. And we get, it's a uv minus integral of v du. So negative t over s e to the negative st uv minus the integral of v du. 1 over s, so minus negative 1 over s is plus 1 over s e to the negative st dt. So negative t over s e to the negative st, sorry, e to the positive st, if we put it in the denominator, plus 1 over s, and then when we integrate this we get another negative s down there, e to the negative st. So we've got negative t over s e to the st minus 1 over s squared e to the st. Alright, that's just the indefinite integral of this, really, plus c. So this is integral of t e to the negative st dt. And when I get rid of the integral sign, I should really say plus c, so that's just the indefinite integral. Now what if we want to evaluate this from 0 to infinity? Then the integral of t e to the negative st from 0 to infinity is the limit as capital N goes to infinity of, we can plug in n and plug in 0 and subtract. So minus t, that would be a minus n, over s e to the sn minus 1 over s squared e to the sn. Now we plug in 0, minus 0 minus 1 over s squared, and then e to the 0th is just 1. So what happens as n goes to infinity? N goes to infinity and e to the Sn goes to infinity. But the exponential goes to infinity faster. So this fraction goes to 0. This fraction certainly goes to 0 because the top isn't increasing while the bottom increases. So that's 0, 0, that's 0. So we're left with plus 1 over s squared. Alright, so L of t, the function t, is 1 over s squared. Now we're looking at functions on an interval from 0 to infinity. I guess we have to exclude the point s equals 0 here. We have to exclude it there also. So this is really only defined for s greater than 0, and this is defined for s greater than 0. Now using integration by parts, we can show that if we want to take the Laplace transform of t to the k, that equals k factorial over s to the k plus 1. So when k equals 1, we have 1 over s squared, which is what we got for the Laplace transform of t here. All right, let's look at another example. Let's look at the Laplace transform of an exponential function, e to the at. So this is the integral as t goes from 0 to infinity of e to the negative st e to the at dt, which is the integral of e to the a minus s t, just combining the exponential functions, dt, which is, let's see, I wish I had a minus s in the integral with me, so this would just be, the integral would just be e to the a minus st. So let me put it there. I'll divide by a minus s on the outside, e to the a minus s t a minus s dt. So this is 1 over a minus s e to the a minus s t as t goes from 0 to infinity. So its limit as n goes to infinity of 1 over a minus s e to the a minus s t as t goes from 0 to n. So let's see, we have 1 over a minus s e to the a minus s capital N minus 1 over a minus s e to the a minus s times 0. The limit as n goes to infinity of this. Now what happens here depends on whether that exponent is positive or negative. If a is greater than s, then we have e to the positive number times n as n goes to infinity, so this is going to explode. It's going to go to infinity. And then, well, e to the anything times 0 is e to the 0th, which is 1. So we can just get rid of this. That's just 1. We have 1 over a minus s there. But this is infinity if a is greater than s. So what happens if a is less than s? If a is less than s, then this is 1 over a minus s. A minus s is negative, so I could write that as 1 over e to the s minus a, and then that's going to be positive, times n, minus 1 over a minus s. Alright, we're taking the limit of this as n goes to infinity. What happens? As n goes to infinity, e to the s minus a n is going to go to infinity. Positive infinity, because this is a positive number times n. So we're dividing by a number that's going to infinity, so that means the first fraction goes to 0. Which leaves us just with the negative 1 over a minus s, which I guess we could write as 1 over s minus a. And for s equals a, we'd have a problem. That would be 1 over 0. So this is defined for s greater than a. We were looking at s equals s greater than 0 before, but we want this to be continuous and defined. So we're going to start after a, not at s equals a, but after a. And if we use integration by parts, we can find Laplace transforms of cosine and sine. I won't do the integration by parts here, but it turns out that if we look at the Laplace transform of cosine of bt, then we get s over s squared plus b squared. And if we look at Laplace transform of sine of bt, then we get something very similar, which is b over s squared plus b squared. And this just comes by using integration by parts. Now, a nice property about the property of the Laplace transform is that it's linear. So that is, if we take a Laplace transform of some function f plus some number c times some other function g. So for functions f and g and a real number c, this is equal to Laplace of f plus c times Laplace of g. And the reason is basically that integration is linear. So if we take the integral from 0 to infinity of e to the negative st f plus cg. That's just the integral of e to the negative stf dt plus c times the integral of e to the negative stg dt, which is just L of f plus c times L of g. Oh, going off the screen. So, just because integration is linear. Alright, so let's do an example using linearity. So for example, if we want to take the Laplace transform of t to the fourth plus 6 cosine 2t plus 2e to the 3t plus 8 then we get 4 factorial over s to the fifth, because Laplace transform of t to a power is that power factorial over s to 1 greater power, plus 6 t over t squared plus 4, because the Laplace transform of cosine of bt is s over s squared plus b squared. So t, oops, this should be a t, this should be an s. S over s squared plus 4, which is 2 squared. Plus 2 times 1 over s minus 3. So 2 over s minus 3, because the Laplace transform of e to the 3t is 1 over s minus 3, plus 8 over s, because the Laplace transform of 1 is 1 over s. Now this would be valid for, let's see, the first fraction is valid for s greater than 0, second one for s greater than 0, third one s greater than 3, fourth one s greater than 0. So this is valid for, we need to take the interval that satisfies all 4 of the fractions. So s minus 3 is going to be the intersection of these intervals, the one that satisfies every fraction. Alright, now all the examples we've done so far involve continuous functions, but the whole point of introducing Laplace transforms was to work with discontinuous functions. So let's do an example with a piecewise continuous function. Let's let f of t be t when t is between 0 and 1, and let's let it be negative 1 for t greater than or equal to 1. So f looks like this. There's no infinite discontinuities. We've got an interval here from 0 to 1 where the function is continuous, and then from 1 to infinity the function is continuous again. Alright, now when we integrate this from 0 to infinity, we have to integrate one function from 0 to 1 and another function from 1 to infinity. So L bracket f equals the integral of e to the negative st f of t dt as t goes from 0 to infinity, which is the integral as t goes from 0 to 1. F of t on this interval is defined to be just t, e to the negative st t dt, plus the integral as t goes from 1 to infinity of e to the negative st negative 1 dt. Now we did integration by parts on e to the negative st earlier. So we said that this integral was equal to negative t over s e to the st minus 1 over s squared e to the st plus c. So that means that this first integral is equal to negative t over s e to the st minus 1 over s squared e to the st, evaluated from 0 to 1. So when we plug in 1, we've got negative 1 over s e to the s minus 1 over s squared e to the s. When we plug in t equals 0, this first fraction is 0, minus 1 over s squared e to the 0, so minus 1 over s squared. Actually, we're subtracting, I should really write minus negative 1 over s squared e to the 0. So we're adding 1 over s squared. Negative 1 over s e to the s minus 1 over s squared e to the s plus 1 over s squared. So that's the first integral. And then the second integral is the integral from 1 to infinity of e to the negative st negative, I wish I had an s here, so I'll put it there and then divide by s on the outside. So this is 1 over s e to the negative st, evaluated from 1 to infinity, which is the limit as n goes to infinity of 1 over s e to the negative s n minus 1 over s e to the negative s times 1. So plugging in capital N, plugging in 1 and subtracting. So this is going to be minus 1 over s e to the s. And as n goes to infinity, what happens to 1 over s e to the sn? Well, as n goes to infinity, this is going to go to 0, so we don't need that. So we just have negative 1 over s e to the s. So adding together the pieces we've computed so far, the Laplace transform of s equals 1 over s squared minus 1 over s e to the s minus 1 over s squared e to the s minus 1 over s e to the s. So I guess we have minus 2 over s e to the s because we saw that twice. And again, these functions are all defined for s strictly greater than 0. We don't want s to be 0. And we don't want s to be greater than or equal to 0 there either. So these are defined for s greater than or equal to 0. Alright, so for now we're not going to use these Laplace transforms to solve differential equations. In another video, we're going to see how we can use these to solve differential equations. The end.